Hey guys, Dr. Thomas. This is part 3 of chapter 1. We are following the PowerPoint. I left off last time right when we got to the periodic table. So there's a lot of information here that we need to talk about with the periodic table. Again, we're going to learn things about the periodic table in chapter 1 and 2. Then we're going to learn a whole bunch more in chapter 7. That whole chapter is about trends in the periodic table and stuff like that. But for now, just need to know kind of just how it's organized. So first of all, the order of the elements: hydrogen's number 1, helium's number 2, lithium's number 3, beryllium's number 4. The atomic number is the number of protons in an atom of that element. So hydrogen atoms always have 1 proton. Helium atoms always have 2 protons. Lithium atoms always have 3 protons. That's the order that the elements are listed. It's very important. Okay. Also, when you look at any element, so the atomic number on this periodic table is on top. Underneath, the mass number is the number of protons and neutrons, although the number on the periodic table. The number of protons and neutrons gives you the weight of an atom, but not all atoms of the element weigh the same thing. There are these things in chapter 2 called isotopes, where you can change the number of neutrons, so you get different weights. So the number on the periodic table is actually the average weight of all the atoms of an element. Okay, so like chlorine has 2 isotopes. One of them weighs 35 AMUs, one of them weighs 37 AMUs. The weighted average is 35.5. Okay, again, that's something we'll get to more in chapter 2, but for now, just know the mass number is the average weight of all the isotopes of an element. All right, now, what's organized, basically, there's a diagonal line sometimes on some periodic tables that goes right through here. Basically, everything to the left is a metal. Everything to the right or above is a nonmetal, and then the gray elements that are touching the line are the semimetals, sometimes also called the metalloids. Okay, property-wise, I mean, you know the basic properties of metals. They conduct electricity. They're hard. They're usually shiny. They're good conductors of heat. All that kind of thing. They can have magnetic properties. Then we have the nonmetals. They tend to be either gases or like powdered solids. And then the metalloids are somewhere in between those things. Okay, we organize the periodic table. The vertical columns are called groups. The horizontal rows are called periods. The periods, we don't do a whole lot with those other than just we know that as we move across the period, the properties are going to change significantly from the left side to the right side. More important though are the groups. Elements that are in the same group tend to have similar chemical properties. So I know that sodium and potassium and rubidium all have similar properties to each other. When they react, they all take a +1 charge when they form compounds. All the alkali metals are really reactive. When you never find them in nature in their pure form, since they'll react with anything around them. So by the time you find sodium in nature, it's already formed sodium chloride or sodium carbonate or something else. You're never going to find just a piece of pure sodium metal. Okay, that's true for all the alkali metals. Group 2 are the alkaline earth metals. They're pretty reactive also. When they form compounds, they always have a +2 charge. So, you know, again, there's commonalities between those. The way we number the periodic table, the groups, there's the A groups and the B groups. The B groups are the transition metals from here to here, or from here to here. And then the A groups are group 1 and 2 right here. That's group 1A and group 2A. And then we jump over to group 3A, 4A, 5A, 6A, 7A, 8A. Okay, now some of the groups have names that we need to know. Alkali metals, need to know that name. Alkaline earth metals, got to know that one. Way over here, group 8 are the noble gases. Sometimes they're called the rare gases or the inert gases. It's all the same thing, but usually noble gases is fine. Then we have the halogens, or group 7, and then we have the chalcogens, or group 6. Those are the groups we need to know. Most of the main elements that we see are in those groups, so that's what they're called, the main groups. And then in the transition metals, which are the B groups, you also do have some important elements there, like copper, silver, gold, nickel, iron. There's lots of common metals in there. Okay, and then finally, the bottom, the 2 rows right here, are called the intertransition metals. they should be fitted in. If I look at number 57 to number 71, if I tried to put them in, they actually go right here for the top row, and then the bottom row should go right here. So if I try to slide them into that spot, the periodic table has to split apart. So actually the true periodic table should look like this. I got my inner transition metals here, my transition metals here, and then group 1 and 2, and then group 3 through 8 are way apart. Now, why don't they show the periodic table like this normally? Well, when they stick that in there, the periodic table gets so wide that they have to shrink everything down. And if you have to shrink everything, it makes it harder to see. And if you made posters and stuff, it just wouldn't be as presentable. So that's why the inner transition metals are usually pulled to the bottom. So that brings us to the next topic, measured numbers versus exact numbers. So we're about to get into the topic of significant figures. To understand significant figures fully, we have to understand the difference between these two things. So first of all, we talk about exact numbers. An exact number is a number that wasn't measured with a tool and wasn't rounded off, okay? So typically, if I'm counting objects, like let's just say I'm in a classroom, and if I count all the students in the classroom, there's 40 students in a class. Well, essentially that's an exact number, as in there's not 40.1 students in the class, there's not 39.8. I didn't round it off or anything. I mean, there's exactly 40 people in there, okay? And I could even say it's 40.0 or 40.00000. I can put as many zeros after the decimal as I want, and it's still accurate because there's exactly 40 people in the room, okay? I can do that when I'm counting whole objects. I can also do that when I'm doing a defined relationship, like the relationship between, in the metric system, if I take a meter, and divide it into 100 equal increments, those would be centimeters. By definition, a centimeter is 1/100th of a meter. That's an exact ratio that we're not measuring it, we're just saying that's the definition of what it is. Okay, we can also look, if we take a foot and divide a foot into 12 equal increments, that would be, each one would be an inch. So 12 inches equal a foot. So basically when I use those relationships, they are not going to be limited by significant figures. You can put as many zeros after the decimal as you want, so don't use exact numbers to limit your significant figures once we get into the next section where we're talking about the rules for sig figs. Okay? Exact relationships are unlimited in sig figs. Now, the other type of number though is a measured number. Anytime I use a tool to measure a value, that's going to be a measured number. Okay, I can use a meter stick to measure how many centimeters or meters something is. That would be a measurement of length. I can weigh something and get grams or pounds, so that's the mass or the weight. I can use a clock to measure time. I can use a thermometer to measure temperature. There are a lot of different things I can measure with tools. And anytime I measure with a tool, I'm going to have to decide when I write the number down, how many digits do I record as I write, okay? And there is a difference in how you write the numbers. If you write too many digits, there's an implication in that you were really careful making the measurement when it may be you just weren't paying attention and you wrote down all the digits that your calculator gave you on your answer. You just wrote everything down and you weren't really thinking about it, and that can be a very bad thing. So, if we make a measurement, so I'm going to take this ruler stick and measure the piece of wood. Essentially what I'm going to do is I'm going to look at this and say, okay, so first I need to look at the measurements where each big number here represents a whole centimeter. So my main markings are in the ones position. 1 centimeter, 2 centimeters, 3 centimeters, 4 centimeters, 5 centimeters. Then my smaller markings, each one of those, the increment is 0.1 centimeters. So I can look at this and say, okay, I know the first digit is going to be a 4, because it's between 4 and 5, so it's going to be 4 point something. And then I can look and say, okay, I know it's between 0.5 and 0.6. So on the first two digits, the ones position and the tenths position, I know that they're both accurate. I'm not messing those up. the markings tell me that those numbers are true. But where I get a little bit of uncertainty is going to be on the third digit, where I'm between 4.5 and 4.6, but I can tell, to me it looks like the stick's about halfway. So if I were going to estimate the digit, which is the hundredths position, I would probably look at that and say, oh, it looks like it's about 4.55 centimeters. The rule that will apply in class, in lab, as you move on to other classes and everything, you record the numbers that are accurate, and you can write down one estimated digit. You can always go one digit beyond the smallest marking. And since the smallest markings are tenths, that means I can estimate the 100. Now, if I'm in between, if I'm halfway, I'd say 4.55. A lot of people mess up. What if it was on the line for 4.5? They'll just leave it at that and say, oh, it's 4.5, and that's the answer. But if I can estimate the hundredth position if it's in between two lines, I can also estimate the hundredth if it's on a line. If it was on a line, I would say 4.50. And that 0 in the hundredth position is a way of telling somebody, hey, it looks like it's right on the line, so that's why I put that 0 there. Okay? So that's very important to think about. So whoever made this PowerPoint, I've tweaked it, but I didn't do this part, is between 4.5 and 4.6. Whoever read this actually thought it was a little more than halfway, and they said 4.57. I said a couple minutes ago 4.55. I don't know who's right, the other person or me. It doesn't matter. The estimated digit is going to have a little bit of uncertainty with it. So it's okay if two people look at the same value and measure it differently. There's not a problem with that because we all know the last digit is the one that's estimated or rounded off. Okay? So now we get into accuracy and precision. I'm going to breeze through this. Accuracy, if you make a measurement, the accuracy is how far off you are from the true value, like what you're supposed to get. The precision, if I make a measurement several times, it's an assessment of how consistent I am. If I make the same measurement and get the same value over and over and over again, that means I have high precision. If I make the same measurement and get different numbers every time, that would be low precision. All right, so I make a measurement, I have to decide what to write down. So let's just say somebody just walked up and asked me how much I weigh. I might look at them and say, oh yeah, I weigh about 170 pounds. And when I say that, I weigh about 170 pounds, what am I implying? The answer is, I'm like, well, it's around 170 pounds, but I probably haven't weighed myself today or in the last week or so, so I'm kind of guessing at my weight. And actually, when I say 170 pounds, we're going to learn the rules for sig figs in a second, but that 0 is not a significant figure. If there's no decimal there, that 0 is a rounded off 0, which means that my significant figures, or my accurate digits, are the 1 and the 7. The 7 is in the tens position. So basically what I'm saying is, if I round my weight to the nearest 10, it would be 170. So that means that I really weigh somewhere between 165 and 175. Okay? That's the range that's implied when I say I weigh 170 pounds. Now, what if somebody walks up to me and I've got a $500 scale that measures my weight to the thousandth of a pound, and I'm like standing on the scale and I read the number and then I step off and somebody says, how much do you weigh? And I'd say 168.968 pounds. And that would only be accurate for a few seconds. Because if I ate an hour ago, as my body digests food and I breathe out carbon dioxide and water, my weight's going to change. So if I write down 3 decimal places, it's only going to be accurate for a few seconds, and it's only if I just got off a really expensive scale, that's the only way it's going to be accurate at all. So which one do I write? Well, if I don't really know my weight, I need to write this one down, or that's what I would tell somebody. If I just stepped off a really expensive scale, then I can tell this one. But if somebody asked me randomly and I said my weight was this and I hadn't weighed myself lately, basically I'm lying. In science, I'm misrepresenting the data if I write too many digits, because it makes somebody think that you use really expensive equipment and you're really careful about how you measured everything, and that's not what I did. Okay, so I'm gonna have to cut off right here because my time is running out. We'll start another video in a second.